Okay, so this recording, we're going to be talking about Chapter 3 and some of the numerical descriptive measures that we're going to be working with. All right, so some of the stuff we're going to talk about in this, we're going to talk about something we call central tendency. So a lot of this is going to be, so one of the things we're going to see in this chapter is a fair number of terms, different things. We'll make note of, we're going to walk through it, all right? So we'll talk about idea of a central tendency, variations, and shapes of numerical data. Remember, we're part of what we're going to do is we have a set population of data that we would draw a sample from, and we're going to do some analysis against it, and then we're going to turn it into a visualization, which will give us a sense of the shape. So the shape tells us a story. So a couple things we'll do. So we said we're going to look at things like central tendency, variation, and shape of numerical data. What we mean by a box plot, which is a form of visualization. How we compute descriptive summary measures for a population. And then also talk about covariance and the coefficient of correlation. All right. So there's a couple things to begin with. So we're here in our Dekova model. So we've done, discovery, collection, organization, visualization. Now we're going to be doing analysis. All right. So there's a couple summary definitions we're going to start off with. First is what we call central tendency. And central tendency is, the description of the extent to which the values of a numeric variable group cluster around some type of central value. Right. So the idea is that there's some percentage of the values. There's going to be a central point. So you think of things as being a central point, then kind of your variations off of it. All right. So the central tendency is the extent to which numerical value group clusters around a central value. Variation is the amount of dispersion scattering away from the central value. So what happens is we have the central value, central tendency around a central value, and then the variation is all the stuff that kind of spreads around it. And then the shape is really the pattern of the distributions of the values, right, running from the lowest value to the highest value. So the idea is these are all designed to give us some indication, some sense of what the data looks like. All right. So there's really three measures of central tendency. They're pretty well known, but we'll walk through them. All right. So one is something we call the arithmetic mean. Second one is something we call the median, and the third is called the mode. All right. So the mean is, we derive the mean. It's the average of, we sum all the values up, and we take the average, we divide by the number of values, and we call this the average. We call this the average, but technically it's the arithmetic mean. The median, on the other hand, is the middle value in an ordered array. So remember, we talked about one of the approaches we take with data is we take a set of data, a sample, or even a population, and we sort it into high-low order, right? And what we can do is if we take the middle value of that, that's what we call the median. And then the mode, which is the third indication or third measure of central tendency, is the most frequently observed value. All right. So in this case, we'll look at each one of these. So this is a very fancy. We see the formula, and it looks impressive, because obviously we have you see sigma, and, what all this really means is we add up all the values. The sigma means sum from 1 to n, depending on how many variables we have. We add them all up of all the values of x1, and we divide them by the number of values. Right? So it's our sample size n. So if I have 500 items, we add up all 500 items and divide it by 500. And that will give us the arithmetic mean. So it's pretty common. So it's very common. We use it. We use this all the time to get at least some sense of what the values of. If I'm looking at some sort of sample, if I look at the average, I have some sense of what its value. All right. And so we said sum of values divided by the number of values. The challenge, though, the problem we run into, though, it can be affected by extreme values. We call them outliers. Remember, outliers are the things that are outside, the things that are farthest away from the central value, either negative or positive. All right. So in this case here, we'll take an example. I have 5 numbers, 11 to 15. I add those 5 together, divide by 5, and I find my average is 13. However, if I have a outlier of 20 in the same population, so I have 5 values, so 11 to 14, and then the 5th value is 20. If I do the same calculation, what you'll find is the mean will shift over one. So what will happen is, if I have extreme values in my sample, then I'm going to end up, we're not going to be as accurate. All right, it will not be as representative as we would like. Right? So you can use it as we can use it as a general term, but there's obviously we always have to be aware of that. Now, what we can do because of this variation problem, problem with extreme values and kind of shifting things around, we can use what we call the median. All right. So what the median is, so we take our ordered array, so we take all of our data, sort it, and what we do is we look for the middle number. All right, where 50% is above and 50% is below. All right. So in this case, in the first case, we have our 11 to 15, median is 13. Right? But if I have the outlier, say I have that 20, my median is still 13. All right. So it's less sensitive than the mean to where if we have extreme values. Once again, it's a matter of kind of understanding the nature of the data we have and what type of, basically what the variability of our data is. So the way we get to the median is we, for step 1, sort it into order, smallest to largest. And if we have an odd number of values, the median is the middle number. So we go right to the middle, and equal numbers to the left, equal numbers to the right. If the number of values are even, we take the 2 middle numbers and we average those 2 together. All right, so that will give us the median. And so it's really a matter of whether our population or our sample is either an odd or an even number. And then we have a third measure of central tendency, all right, which is what we call the mode. And the mode is, we define that as it's the value that occurs most often in the distribution. So so what we'll do is we're looking at our sample and we're actually collecting, the count of all of these different values. All right. So it's it really it's not affected by extreme values, and you can use it for numerical. We can use it for categorical. Right? When the problem is there might not be a mode, or there might be several modes. All right. So in this case here, well, 9. As we look at this, so the one that has the most is 9. So the mode would be 9. All right. However, if I have my values here, I only have one of each, then there's no mode. All right, just something to be aware of. All these things are possible. So really, it's a reflection of what we have in the data. All right. So example here, we'll do if we take a example, house prices. All right. So we have kind of an extreme value here, kind of an outlier, 2 million for the one house price. And then the rest of the house prices are kind of close. So it's 100,000, 100,000, 300, 500,000. Right. We add them up, divide by 5, get 600,000. All right. The median, though, so the 2 million really, if you look at this, it probably has thrown this off because actually the mean in this case is actually higher than the majority of the values. So in this case right here, the median, which is the middle value, 100 to 100, 500, 2 million, the median is probably more representative of the data, of the distribution of the data, of the central tendency. And then the mode gives us the most frequent value. All right. So all three of these are all three different techniques. Each one has a particular use case where it's most valuable. So which one to use? Right? If we're analyzing discrete numerical data, the mode works best, or the mode is a good choice. Right? We use the mean and the median in cases where we have continuous numerical data. All right, so we use the mode. Usually, we'll use the mean, unless we are detecting extreme values, at which point we would switch and use the median. So really, the median is the use case for the median goes around outliers, where we have outliers. And in some cases, maybe it may make sense, depending upon what we're trying to do. It might make sense to use both. So it's not an either or proposition. We can use either one or the other, once again, depending upon our use case and what we're trying to analyze. All right. So let's talk about variation. So we kind of talked about the central tendency, right? So which is this kind of the center, right? But then we have all of the values, and where are the values actually located in relation to the center? Right? So that's what we call variation. Right. So we focus on the spread. A couple different ways we can call it. We call it the spread. We call it the variability. We call it dispersion. All of them kind of have to say the same thing. All right. And the measures of variation we have the range. We have what we call variance. We have standard deviation, and then finally we have something called coefficient of variation. So let's walk through each one. Let's kind of see what we have here. But as you can see, just to show you here, we have the same center value for both of these, but the distribution of the data is very different. This was much more narrow, so less dispersion here around the central value, versus this one where it's much more spread out. Okay, so we'll look at some of the measures and some of the stuff we do with that. So the range. So we've talked about range before. All right, so the range is, it's the simplest, but it's the difference between the largest and the smallest value. All right, so in this case, so what we'll do is we sort it into, we'll take our data, sort it high-low, take the highest versus the lowest. All right, take the largest, subtract the smallest, and that will give us the range. All right, so in this case here, our highest value is 13, our lowest value is 1. 13 minus 1 gives us 12. All right, so it's a very simple thing. We've looked at this before. It does, once again, it's an easy way to get some information about kind of what the nature of what we're dealing with. It doesn't tell us everything, but it gives us at least a starting point. Now the problem is, it's simple, which means that depending upon the circumstances, they could be, it could have pretty good utility, or depending upon this whole question of the distribution of the data. So if the data is distributed, the range gives us kind of an idea of the scope, but it doesn't necessarily tell us what it looks like inside. So in this case here, I have 12 and 7. All right, so our range is 5. All right, but I have one value, from 7 to 12. Okay, in this case here, I have 7 to 12, but my 12, actually I have multiple values for 12. And so this is actually tilted, the distribution is actually tilted towards the 12 off the center value. All right, so that would be, So that's going to be, in this situation here, this, the range might not give us a good, we can use it as maybe just as part of it, but it doesn't really give us a picture. So, this whole question, the thing we're always concerned about is, what about outliers, and what is the sensitivity to outliers? And you can see we kind of an extreme value here, more of an extreme case here, where if I have a range of, it's like 1 to 5, looks pretty good, all right. If I have a range of 1 to 120, of which, 120 is the last value, well, that's a pretty, that's pretty distorted. That does not really reflect, the range does not really reflect the composition of the numbers. We just have an outlier here that's tilting things, in another direction. All right, so in those cases, what we want to do is, building on the range, what we're going to want to do is we want to develop some calculation, some measure of the variance. All right, so the algorithm we use, or the formula we would use to do this is, we take the average of what we call the squared deviations from the mean. All right, so once again, we have kind of a fairly sophisticated looking formula here. So it's the sigma x minus x, xi minus x squared over n minus 1, where x is the arithmetic mean, n is the sample size, and xi is the value of the variable. Let's look at it in, and then we'll take a look at how we'll calculate that out. And then with the variation, and then on top of the variation, all right, in top of the variance, sample variance, we have what we call the standard deviation. All right, so standard deviation is really the most commonly used measure of variation. All right, so it shows us, and what it is, it's designed to show us the variation around the mean. It's the square. So what we do is we calculate the variance. If we take the square root of that, that gives us the standard deviation. And here's the formula for that. So this, if it looks familiar, it's basically this. It's the formula for the variance, and we take the square root. All right. So let's actually look at it as an example. So it's not as complicated as it looks. All right. So what we have is we have a mean of 16. All right. We have a population, our sample size is 8. All right. So we have 10, 12, 14, 15, 17, 18, 18, and 24. All right. So what we do is, for every value here, what we do is we subtract it from the mean, and we square it, right? And then we do it again for the next value, and we do that for the next value, and then we add all of these values together and divide it by n minus 1. All right, and that will give us the standard deviation. Oh, excuse me, then we take the square root of that. That gives us the standard deviation. So it looks, at first glance, the formula looks more, imposing than it actually is. It's actually pretty straightforward. We simply take our sample data, and for each value, we do a calculation of, subtracting it from the mean, squaring it, summing everything together, dividing it by n minus 1, and then taking the square root. All right. So these are the ideas of variations are comparison of standard deviation. So we're calculating the standard deviation. And standard deviations are, basically derivative of the distribution and the shape of the data. So we can have smaller ones, we can have bigger ones, right, depending upon what we have in the data. Right? In this case here, for this value right here, our standard deviation is 4.3, 4.31 if we average it up. right? So the size, whatever we calculate, will be a function of the data that we're working with. Mm-hmm. But what we will see is the more the data spread out, the bigger the range will be. Also, the greater the variance and the greater the standard deviation, because the range, the variance, and the standard deviation are all, kind of tied together. Right? The more the data is concentrated, the smaller the range, the variance, and the standard deviation will be. Right? If I have a situation where all the numbers are exactly the same, so if everything was the number 2, all right, we would have, the range, the variance, and the standard deviation would all be 0. All right. So it's a reflection of how it gives us a relative measure of how spread out the data is, and also to remember that if none of these measures are ever 0. All right. So there's no, or excuse me, are or ever negative. They can go to 0. It's between 0 and greater than 0. So the coefficient. So a couple more things around the or measures of variation. Let's talk about the coefficient of variation. It's another measure of variation. In this case, though, it gives us what we call relative variation, which is a percentage. And what it is, it gives us, it shows us variation relative to the mean. So, where this comes in handy is if we calculate this relative variation, we can use it to compare the variability of 2 sets of data. All right. So, CV, or as we say, our coefficient of variation is the mean divided into S times 100. So let's S being the standard deviation. All right. So let's look at how this formula actually gets applied. So in this case, we have a situation. Average stock price is 50. So that's our X, right? The standard deviation, which is S, that's S. All right. So if I divide 50 into the standard deviation, which is 5, multiply times 100, that tells us, we have a 10% coefficient of variation. All right. And so we'll do this for one stock. And let's do it for another stock. Another stock, the average price is now 100. All right. Instead of 50, it's 100. All right. Do the same calculation. Divide the average price into the standard deviation. Multiply times 100. That gives us 5%. All right. So what is that telling us? All right. So in this case, we're going to compare 2 stocks. Both stocks have the same standard deviation, but B is less variable relative to its price. All right. So once again, it's a relative measurement that we can use to compare the characteristics of 2 sets of data. Now we talked about the shape of the distributions. Remember, what we're trying to do is we take this blob of stuff, our data, and when we do some analysis for it, and ultimately what we want to do is we want to visualize it such that we can get an idea of what the shape is. The shape tells us a picture. All right, so by doing the calculations and drawing a picture, we can we can visualize what's going on with the data. All right. So the shape of the distribution describes how data is distributed. The 2 shape-related statistics are the 2 things we're going to look at. One is something we'll call skewness. Skewness measures the extent to which the data values are not symmetrical. And we'll kind of look at a picture of that in a second. And the other one is something we'll call kurtosis. All right. And definition of kurtosis is the peakedness of the curve of the distribution, how sharply the curve rises approaching the center of the distribution. So let's look at some examples. All right. So for skewness, all right, skewness measures the extent to which data is not symmetrical. All right, so if we have a symmetrical distribution of data, which we've got a relatively even distribution on both sides of the mean, or the median, or the mean equals the median. We'll do that. So our average is equal to our center value is equal to our average. All right. Then the data is described as being symmetric. So we have an even distribution on both sides. All right. If the mean is less than the median, all right, what that means is we have left skewed data. So here's our median, and here's the mean. So if the mean is to the left, that means we're left skewed. And conversely, if the mean is to the right of the median, that means it's right skewed. All right. So it's really just a picture of what the shape looks like, how things are, we have more on one side than more on the other. So not only are we have an idea of what the center values are, and then where all the data is at. Is it on one side, is it on the other, or is it symmetric? So in this case, as you say, from the statistic is, it's less than 0, it's left skewed, greater than 0, it's right skewed, and symmetric is 0. All right. So if I take the mean, so if I want to do a calculation of this, if I take the mean minus the median, all right, the mean, which is the average, median, central value, mean minus median, divided by what we've calculated as standard deviation, that will tell us what the skew is. All right, and the way we would interpret it is if it's 0, then we're symmetric, kind of within that range. If it's negative, all right, that means it's left skewed. And if it's positive, it means we're right skewed. All right, so this will be positive, right skewed. Negative, when we do that calculation, if it comes out negative, it's going to be left skewed. And once again, it's just a way of being able to draw a picture of the way the data is distributed. Now, kurtosis, which is a fancy term, but basically what it means is it measures how rapidly the curve rises as we get to the middle. Kind of the shape of, so it refers to the shape of the curve. All right. So the idea is this middle one is our normal distribution, where we have our symmetric data. All right. That's just what we call a normal distribution, or a bell-shaped curve. All right. Equal values on both sides of the middle line. A sharper curve, like a sharper peak, means that kurtosis is greater than 0. The formal term for that is leptokurtic. All right. If it's flatter, lower than a bell-shaped curve, then it would be platykurtic. And then if it's bell-shaped, it's mesokurtic. All right, so this would mean, so the definitions of these are, are mesokurtic means kurtosis is equal to 0. Leptokurtic means kurtosis is greater than 0. And platykurtic means kurtosis is less than 0. Right? But it just refers to the way these curves are shaped out. All right. So these are all characteristics. These are all descriptive characteristic statistics that we can use to describe our data. So if we take this set right here, we can take this set of house prices. Right, so we've seen this before. This is our fairly distributed kind of skewed data. So we've got a 2 million up front, 100,000, 300,000, 500,000. So we did this before. If we go through all of our different calculations here, our max, min, range, we can do all of these calculations, all these characteristics. And what it does is, this is what we call descriptive statistics. Essentially, all of these things make up the descriptive statistics for a set of data. So we have our mean, standard error, standard deviation, variance, kurtosis, skewedness, range. And as I said, they're relatively simple calculations. I mean, you have to look at, you look at them at first glance. If you look at the formula looks more complicated than it really is. These are actually fairly simple, fairly straightforward algorithms to implement. So look at some more measures. So there's a couple, there's some other things we can use. There's other measures we've developed, which will, we can use for give us some sense of what a non-central distribution of data would look like. So there's something we'll call quartiles. All right. So what we do is we take so once again, we starting point, we sort our data high-low, and we divide it into 4 segments with an equal number of values per segment. All right, so 25, 25, 25, 25. All right, and then we have 3 marks. All right, so we have a quartile mark, quartile 1, quartile 2, quartile 3. All right, and what happens is quartile 1, 25% of the observations are smaller, and 75% are larger. So quartile 2 is the same as the median. So 50% of all observations are smaller than 50, and 50% are larger. If we look at this as, here's our 25% here. So 25% here, 75% here. It's delineated by quartile 1. Quartile 2 is the same as the median. 50% above, or excuse me, 50% below, 50% above. And third quartile is 75% below, 25% above. All right, now how would we use this? Let's take a look. Let's look at an example here. All right, I have 9 values. All right, so my quartile 1, my dividing line here, it's going to be 12.5. All right. Q2, which is our mean, it's going to be 16. All right. And then quartile 3 is going to be 19.5. So this is only the remaining 25%. Everything below 19.5 makes up the 75%. So 75, it's 25, 75, 25, 75. And then 50-50. All right. Once again, our first step is always going to be in these situations. So we want to sort the data. We want to create a sorted array. All right. So now what we can do is we have something we call quartile measurements, or IQR, the interquartile range, which is an estimation of the spread of the middle 50% of the data. All right, so if we take, Q3 minus Q1, the IQR, it measures the spread in the middle 50% of the data, or we call it mid-spread. IQR, it gives us a measure of variability that is not influenced by the possibility of outliers or extreme values. All right. So the term we use, so things like Q1, Q3, IQR, these values here are called resistant measures because they're not influenced by outliers. All right. So it gives us when we look at it, we have a better sense of the true distribution of the data. So we'll take an example here of our 12 going from 12 to 70. All right. So what we have is so remember the bottom, it divides into four quarters, 25, 25, 25, 25. Delineation, the first 25%. We take our range. So we're, what we want to do is we want to have our range of numbers goes from 12 to 70. 12 to 30 makes up our first quartile. All right. 57 to 70 makes up our third quartile. And then the interquartile range is 57 minus 30, which is 27. So we identify our marks, the marking points for 25 and 25. And then what we have in between, we subtract the high range from the low for the interquartile range, and it'll tell us it'll give us our interquartile range calculation. All right, so what we can use is, we call this, the term we use is what we call a 5-number summary. Right? So the 5 numbers describe the center, the spread, and the shape of the data. The 5 numbers. So if we calculate these 5 numbers, we can get a picture of how this data shapes up. All right, so we have our x smallest, or basically the range. So range is the largest versus the smallest. We calculate our first quartile number, is 25%, 75% greater. We do the median, which is the midway point, 50%, 50%. Third quartile will be the remaining 25%, above the first 75%. All right. If we calculate these numbers, this gives us what we call the 5-number summary. And what we do with the 5-number summary is we use it to generate what we call a box plot. So it's a graphical display of the data based upon our 5-number summary. So here we go. As we can see, once again, here's our 25% here. Here's our range, smallest and largest. Here's our 25% of the data, 25% of the data, our Q1 or Q3, Q2 being the median. All right, so we're just taking our range, sorting it into a range, and then just kind of blocking it out, chunking it out into different percentages. And then we can do a picture. We can do a distribution shape of that, and we can also do a what we call a box plot, which actually gives us a pictorial representation of what this looks like. All right. So left skewed data, right, means, remember, we have more values to the left than to the right. And this actually gives us a representation. All right. This is our mean, more to the left than to the right. Symmetric, equal distribution on both sides. Right skewed would give more on the right than there is on the left. And we can use it, and this gives us kind of a chart. So this gives us our overall range and kind of how the data is organized within that range. All right, so the box plot is sort of gives us another representation of what the curve looks like. As you can see, of the skewing of basically where the data is skewed at, and also how it's shaped. And then, or the other terminology we use is box and whisker plot. They're both kind of the same, but this is based upon. So if we take a look, we look at how the data is skewed of a set of students, male versus female. All right. And what we'll see is we can see the distribution of the male students. It's pretty, looks to be pretty symmetric. All right. Whereas for the female students, we're more skewed. So actually, if we look at our number here, it's 4. So we're seeing the level. You can see just from pictorial representation of how the data is shaped up and how the level of skewedness we have in it. So everything we've been talking about up till now has really been talking about samples. So what we do is we have a population of size n, and then we take a sample of size, small n, capital N or small n. So all these different descriptive statistics we've talked about describes a sample, not a population. All right. So what we'll do is we can do the same thing. We do the exact same thing for a population that we do for a sample. All right. Except that we call them differently. All right. So if we use when we're dealing with a population, summary measures for a population, we call them parameters, right? And we have Greek letters assigned to each one. So the ones we're most interested in, the ones that have the most value, or the things we're most interested in, are the population mean, the variance, and the standard deviation. So it sounds, like I said, a lot of the stuff we see for populations echo what we do for samples. All right, so it's not that much difference. So we'll look for the mean. All right. So the mean, the population mean, is the sum of all the values in the population divided by the population size n. All right. And what that does is we define that gets defined if the population mean is defined as mu. All right. So mu is equal to the population adding all the values in the population, dividing it by the number of values in that population, which gives us the population mean, which is called a mu, which is different than the sample mean. All right. N is the population size. X is the individual values of all of the variables we've collected in that population. All right. As I said, it looks imposing, but it actually is, it's pretty simple. All right, so if I want to calculate the variance of this, the variance of the population, it's the average of the squared deviation of values from the mean. So the deviation of values from the mean is each value minus mu squared divided by the number of values. All right, so that's mu. It's what we call that segment. I'm not sure what that looks. Actually, I have to go back and look at my Greek alphabet. I'm not sure what that symbol is. So, all right. Anyway, but that is the population variance. And if we go back and look, it looks the calculation is very similar to what we do for sample variance, right? Except that we're drawing from a different size, size of data we're pulling from. All right. And then the population standard deviation, all you do is we take our variance, we take the square root of the variance, and that gives us our population standard deviation. All right. And what it will do is it will give us it will give us a measure of the variation around the mean. So it's the square root of the population variance. Or the standard deviation, or the way we would describe it is the standard deviation squared is the variance. The square root of the variance gives us the standard deviation. And the standard deviation, we'll kind of look at as we look at our different variables here. So it's samples and populations. Pretty much the same. So we got, for populations, mu, variance, standard deviation. Sample statistic is, we represent it as an X bar, S and S squared. All right, so, but just think of the standard, the variance is the standard deviation, is the square of the standard deviation. The deviation, standard deviation, is the square root of the variance. So this standard deviation is very useful because we can use it for, we can use this as to give us a kind of be able to do an empirical evaluation of our data. All right. So if we have, say for example, a bell-shaped distribution, a normal distribution around our mean. All right. We approximate 68% of the data in a bell-shaped distribution is within one standard deviation of the mean. All right, so it's the mean plus or minus one standard deviation. So at 68% of the data. So that's how we use our plus or minus. Furthermore, we can say that 95% of the data, if we have once again, if we have a bell-shaped curve, 95% of the distribution lies within two standard deviations of the mean, or mu plus or minus two standard deviations. And in third, 99.7% of the data in a bell-shaped distribution lies within three standard deviations of the mean. All right, so if I calculate my standard deviations and I have my mean, I can say 99.7% of the data is going to lie within this particular range. It's a pretty good number. That's a pretty, 99.7 is a pretty high number. 95 is a pretty good number. 99.7 is pretty good. And what happens is we can back this up statistically, or we can back this up mathematically. So, and we call this the empirical rule. So it's kind of a rule of thumb, but it's it's a very useful rule of thumb to get an idea of what data looks like. So we'll do a quick example. We're using it. So we'll take our math SAT scores. Don't forget, this is all assuming that the curve is bell-shaped. All right. So it's a normal distribution, mean of 500, standard deviation of 90. Okay. So what that means is, if I have those numbers, what it means is 68% of all test takers, approximately 68% of all test takers, score between 410 and 590. It's 500 plus or minus our standard deviation. All right. 95% of all test takers score between 320 and 680. All right, which is our mean plus or minus 2 times the standard deviation. And then 99.7 of all test takers score between 230 and 770. Right, so that actually gives us a 99.7 estimation of our range. All right, which is 570 plus or minus 270, or 500 plus or minus 270, as we can see that here. All right, so this is an empirical rule. All right. So when we look at the measure, so we can use a couple different techniques to kind of do evaluations. We've talked about scatter plots. that we can visually examine the relationship between numeric variables. We can do a similar sort of evaluation using a numerical measure. All right, so and that's really what the covariance and coefficient of correlation are. So they're the numeric versions of showing things on a scatter diagram or scatter plot. All right, so let's take a look at that. So the covariance, it's the strength of the linear relationship between two variables. All right, so if data moves one way, what will the other data do? All right, so our covariance is our, the calculation once again. And if you look at these actually start looking familiar, right? So this is, the value, minus the mean of the one value, the value minus the mean of the second one, summed together, and then ultimately divided by n minus 1. All right, so I have two, so we have a population of n variables, all right, for x and y. So we have n x variables, n y variables. We know what the mean is, all right. So I take each variable, subtract it from the mean of that for this, take this variable, subtract it from the mean, multiply the two together, sum them up, and then ultimately divide everything up in minus 1. And what this does is it gives us an estimation of the strength of the relationship. Right? It doesn't tell us anything causal, but it tells us what the relationship is between the two numbers. And we call that the covariance. So let's interpret our covariance. Let's do some our covariance interpretation. So if the covariance we calculate is greater than 0, it means x and I are moving in the same direction. If the covariance is less than 0, then they move in opposite directions. And if the covariance is equal to 0, it means the two are variant. It means the two are independent. It shows the relationship. The problem is it doesn't show us, it gives us no indication of the relative strength of the relationship. It tells us what the size is. It'll tell us what directions they move in. But it will not necessarily tell us the strength of the relationship. For that case, we use the coefficient of it. So what we'll do is, we do covariance, and the coefficient of correlation will measure the strength, all right, not of the relationship. This tells us, what the relationship is, or kind of the direction of the relationship. Coefficient of correlation tells us what the strength is. All right, so as we can see, once again, another fairly sophisticated appearing calculation, but the reality of what it's doing is we calculate the covariance first. All right, that's this. And if we take the covariance, right, and we take S, which S, if you remember, is the standard deviation. Go over here. Standard deviation of X and standard deviation of Y. All right, so right here in order to get this, what we do is we'll first calculate the covariance, calculate the standard deviation of one, calculate the standard deviation of the other. All right, and then we'll multiply the two standard deviations divided into the covariance, and that will give us this the coefficient of correlation. All right, so in this case, the population coefficient is referred to as P, and the sample coefficient once again, this is population. Sample versus population. So remember, there's two separate units we're evaluating, either doing it against the population or we're doing it against the sample. We can calculate a coefficient of correlation for either one. All right, so if we're doing it for the population, we call it P. If we are doing it for the sample, we call it R. And P and R will have the following characteristics. Unit free, the numbers will range between -1 and 1. So -1, 0 to 1. The closer to -1, the stronger the negative linear relationship. The closer to 1, the stronger the positive linear relationship. And then closer to 0, the weaker the linear relationship. All right, so each one of these, the number we calculate, gives us an indication of the strengths of these relationships. So we'll use a rule of thumb. So if we use our kind of interpolation of this. If it's between 0 and 0.4, we say there's a weak linear relationship. All right. If it's between 0.4 and 0.6, we say there's a moderately strong linear relationship. If it's between 0.6 and 0.8, we're saying it's a strong linear relationship. And if it's between 0.8 and 1.0, it's very strong. All right. So once again, these are all estimations. These are all approximations, looking at the data, but it's based upon, an evaluation of the characteristics that we've gathered within this. All right. So if we plot this out, all right, so there's a shape of the curve. So if we actually plot these data out with different coefficients of correlation, a downsloping curve, all right, with our following the line, shows us a -1. So we said -1 or 0.1. 0.1, which is going to be a relatively weak linear. What was it? It should be force -1. Relatively weak. 1 is strong. 0 is even. 0.3 is, so these are all, the upward curve is indication of strong. All right. Downward curve is indication of weak. All right. And then on the line right here, this is indication of an equal. All right, the weaker relationship. All right, so we said between minus and -1, closer to -1, stronger than negative linear relationship. So monitor 1, so the linear relationship is downward, so this is indicative of a weaker relationship. This is a little bit stronger, but it's still in a negative sense. Upward curve, this is a very strong linear relationship, and this is not quite as strong, but it's an upward curve, but not as strong. Right. So the interpretation of this, right? How do we use this? So really, so it's a number. So we generate a number, and say in this case, say for example, we've got a 0.7. We look at this plot distribution. We calculate 0.733. All right. So 733 means that's it's greater than 0 but less than 1. which means that is so the curve for 0.733, all right, is going to be, it'll be closer, it'll be between this and this. So you'll see more, it'll be a little bit more distributed. The curve will go up, and a little bit more, there'd be a tighter distribution around the line than there would be here. All right. So if we say 0.733, there was a relatively strong positive or linear relationship between the test score 1 and test score 2. And what that means in real life is, what we can use to interpret that as, is the students who scored high on the first test also tended to score high on the second test. All right, which means that, an indication, if we have one value, that gives us an indication of, relationship to the second value. All right, so that is an overview of our, the different, our centeredness, our, the overall kind of how we look at how we can take data, apply it, structure it, and be able to do interpretations against it.